Okay, this is Introduction to Statistical Learning, Chapter 10, and we're just starting the applied questions, and we're starting then with question 6. So here's what we have. So we're basically going to try to implement a version, well, not a version of gradient descent, but not on messy, noisy data on an exact function, right? Normally, normally we are maybe applying gradient descent on a loss function or something like that from messy data, and we're trying to find the best fit that we can. But here we have a very definite path to carve out, and so A through D just give us steps to doing it. Okay, so in part 1 or in part A, we are just meant to draw a graph of the function being sine of beta plus beta over 10, where beta ranges from -6 to 6. And so I just have beta here. And there's different ways you can do this. But the way that I've done is I've actually made beta values, 100 beta values between -6 and 6, and then just written my function called R beta, and then we can plot it. And we get this guy. Next, part B, we need to determine the derivative of the function. And so this is not a calculus course, but hopefully you're familiar with derivatives. And so, we take the derivative with respect to beta of sine of beta, and that's cosine of beta. And then we take the derivative of beta over 10 with respect to beta, and that's 1 over 10. And so our derivative is cosine of beta plus 1/10. Okay. And now in parts C and D, we are actually going to write some code to perform gradient descent. And when we do this, we will do one pass where we start at 2.3, that's beta naught, and then for part D, we will start at 1.4 instead. So there's a few ways that you could do this. And I guess just out of fun, more than anything, I've tried to write a pretty general function here, where I can pass this function, this R function, my mathematical function, f, its derivative, an initial starting point, a learning rate, rho, which here we're going to set to 0.1, and then we will run the algorithm that we'll see below until a tolerance is reached. And so this tolerance will say when two consecutive iterations are within a certain tolerance, we will stop the algorithm, or it stops after a maximum of 100 iterations. Okay, and then we'll plot it, and we can also tell the function, the domain in which to plot. Okay, so the function is all here. So I'm going to set a empty vector for my betas, and then I'm going to fill that up with the code below, or part of the code below, and then we start the first beta 1, with the initial value, okay, that we pass to the function here. And we run this while loop, and it says while the difference between iterations, between between the previous beta and the next beta, or in the present beta, while that is less than some value, the tolerance that will be set up here, then run it again, basically. Okay, and so what are we running? Well, we're saying we'll take the beta, and this is the gradient descent part. We take the beta that we previously found, and then subtract the derivative scaled by the learning rate, right? That's what gradient descent is right there. And we just run that over and over and over, and then when the difference between consecutive betas is small enough, we halt. Okay, and then after that, we plot the function, and that's what the rest of that code is doing. So I think that's probably a little bit more self-explanatory, so I won't go through it. So we have it for 2.3. So so first we need to load the function. So the function is loaded, and then we're going to run it for initial conditions 2.3 for part C, and then 1.4 for part D. So in both cases, the function I'm going to pass is that right there, the beta, sine of beta plus beta over 10, and we already know the derivative. We found that earlier. And so we run that, and here's our plots here, okay? So for part C, where we start at 2.3, so here's 2.3 roughly here, right? We see that the algorithm takes us down the gradient. It descends the gradient to this local minimum, or at least a very good approximation of the local minimum. And then if we run at, or if we start at 1.4, somewhere here, now we're actually on the other side of this local maximum. And so when we start going down, we find ourselves in a different local minimum, way down here. Okay. Just out of interest, it is kind of cool to play with some of these parameters here and just see how that affects the fit of everything. So if we take it up to 0.5, we still converge to the minimum. So that's kind of cool. Maybe let's see what happens if we go all the way up to 1. See if we start getting this weird overshoot. If we, okay, so not bad. And then we could also take this, so we could keep going up and up and up. But let's see what happens if we go way down. I wonder if we'll time out of our 100 iterations. Yeah, so now the learning rate is so small that we burn through our 100 iterations incredibly quickly, and so we never reach the bottom. So anyway, let's just for fun set these equal to 10, just to see what happens. Yeah, so interesting. So now the learning rate is so large that as we are, trying to make our gradient descent, we're continually overshooting. We're overshooting the local minimum, and then the algorithm tries to recalibrate, and it just goes all over the place. So that's kind of interesting. But anyway, we will call that good, I think.